Okay, one more video here. So these alpha waves were the first to be discovered. That's why they're called alpha. They were discovered by Hans Berger, as we mentioned in class, in his secret laboratory where he was trying to investigate the biological underpinnings of telepathy. And he found that if he could stick electrodes under the skin of willing subjects, he was able to observe 10 times a second wave in their EEG, especially when they stopped focusing on anything and just let their minds wander. So he found these high frequency, low amplitude beta waves, and then when people stopped paying attention, he found their brains switched into this state of alpha waves. And so here's some extra information about Hans Berger if you're interested. For instance, that he didn't seem to know very much about electricity itself. Whereas he was pasting out his data onto paper and analyzing it with rulers, we can use mathematical techniques to investigate oscillations in the brain, because we can take advantage of this technique called the Fourier Transform, which takes any numbers over time, like the stock market or the weather or the brain activity, and it looks at which sum of which sine waves could be used to make up that wave. And so in this case, this low frequency wave has a high coefficient here because it has a big influence on this final product. So you get these values called coefficients, which indicate the amount of each of these different frequencies of wave in the data. So we can use that technique to, for each chunk of EEG data we might have in our data set, instead of averaging them together, we can compute the different frequency responses in that data. So we can look at oscillations of different frequencies. Here's frequency on this axis and power is shown on this axis, or how big the waves are. We see that we can have a peak at 10 hertz normally in humans. This is the alpha waves. So we could then identify that peak for each trial and measure how big it is and compare it between conditions. We could also compare which part of the cycle people are in at any given part of the trial, whether they're at a peak or a trough, if we want to answer other questions about the oscillation. A very classic finding now about alpha oscillations is that they're bad for seeing things. The bigger they are, the harder it is to see. So here we can see that if you compare the spectra when people did and didn't see a very faint flash of light, there's much larger alpha waves when they didn't see the light compared to when they did over the back of their heads. You can also create an artificial flash of light with magnetic stimulation. So you can use a TMS coil over the visual cortex to make people see a little flash of light sometimes, and you can compare when they did and didn't see it. And when they didn't see it, it was because their alpha power was higher in the 250 milliseconds before the onset of that stimulation over the back of their head again. So the bigger you have these alpha waves, the worse you are at seeing the world. We showed the same thing in this experiment in which we showed a target followed by a donut that makes the target very hard to see. We found that the bigger people's alpha waves were, the less likely they were to detect that visual target. And so as you're driving home this afternoon, or as you're going to work tomorrow, you can imagine times where you have high and low alpha waves, and you're going to be more or less responsive to the world around you. Just like with the light, we can create very thin, flexible electrodes to do EEG with. So we can paste these electrical systems onto skin. This one has wireless transmitted power and wireless transmitting data, and it measures the electrical potential between these two parts of the body. So we can put that on the head and measure the electrical activity of the brain, much like we've been talking about today. We could even print it onto more robust material like hockey tape, like stick tape, and allows you to wear it for multiple days and used in situations like driving. Finally, I wanted to show you this progression of EEG equipment throughout the last 100 years, from the whole room full of equipment that Hans Berger would have needed without computers, down through someone who worked in his lab, Donald Lindsley, who brought EEG to America, to his student, Manuel Donchen, who just passed away this year, who was a popularizer of EEG and BCIs, and who would have used a system like this that takes up a whole cabinet size part of a room, to my advisor, Monica Fabiani, who was Manny Donchen's student, who had a system like this when I got to the lab that would sit on a table and be powered by the electricity in the room. When I started my job as a professor here, we finally had the ability to record wirelessly and transmit the data wirelessly across the room. Not only that, but we have these consumer grade EEG devices that are much less expensive than the $30,000 equipment and the $100,000 equipment shown here, and therefore can be used, for instance, in a whole class full of people. And I'm excited about the future of portable EEG as well, and how we can make these devices even more robust. So before the end of this lecture, I also wanted to send you over to eegedu.com, which we're going to be using for the lab. And I want you to start following this introduction module so you can connect simulated data, and you can walk through a little bit more recap on the generation of EEG, the hardware and software involved, and the specific device that we're going to use so that you're ready for the lab coming up next week. We just got our Muse devices shipped to us today, and so we have a set of 50 of them ready to start in the lab next week.